Hi, everybody, and welcome to today's webinar on designing 5G networks. My name is Kelly. I work in marketing here at IBWave, and a big thank you to everyone who's joining us today. We hope that you find the content valuable. Before we get started, I just want to go over a couple of housekeeping items with you. We are going to record the webinar, and everyone will be sent a copy of that recording after the webinar is completed. And we are going to take questions as we go, so please feel free to use the question box in your GoToWebinar panel, and we'll get to them as we can. Lastly, I'm going to introduce today's speaker. So today's speaker is Vladan Jevremovic. He is our Senior Director of Research here at IBWave. He brings with him a deep technical understanding of 5G technology, and he's here to share it with all of you today. So Vladan, over to you.
Thank you very much, Kelly. Hello, everybody, and welcome to our 5G design webinar. This is our agenda, over which we will go in the next 40 to 45 minutes. I'm going to talk about most important new features in 5G. Then I'm going to spend majority of the time talking about specific 5G design practices. Most of them revolve around millimeter wave because it is really the most interesting new feature and the feature that makes the most difference with respect to what we are used to seeing at the frequencies lower than 6 gigahertz. At the very end, I will give you a short demo that will put to practice those best millimeter wave design practices that I will be talking just before the said demo that will include designed network at millimeter wave frequencies. So let's get started with the most important new features. Number one is we have two different frequency bands. The one that we call FR1 in this nomenclature is the one that is between 450 megahertz and 6 gigahertz. And this is the frequency band that you are used to seeing. Namely, so far, everything has been deployed between the frequencies of about, I would say, 600 megahertz in the US, up until about 3.5 to 3.7 gigahertz worldwide. And that would be FR1. FR2 is what we colloquially call millimeter wave frequencies, and it goes from about 24 gigahertz to about 52 gigahertz. And those frequencies are good for designing large networks with a very dense number of subscribers. Dense in terms of the number of subscribers per square meter. And those are stadiums, convention centers, and other various hotspots. Whereas FR1 is used for citywide coverage. Then the next important new feature is 5G numerology. And numerology is just a fancy way of saying we now have different subcarrier spacing and slot duration configuration within our frame. Okay, so LTE, if you look into from that point of view, has only one option at numerology, and that is because the subcarrier spacing and slot duration option, there is only one, which is subcarrier spacing of 15 kilohertz. And 5G has many. So why? Why do we have to have that? Well, numerology gives us flexibility when it comes to latency. And we need that because if you look into 5G as a highway, then when you observe the traffic on a highway, you see different vehicles. There are, motorcycles, there are sports cars, and there are large trucks, and there is everything in between. And you can view the numerology as different types of transportations on that 5G highway. And I am now listing those different numerologies in this table, and you will see that we can go from 0 to 5. Number 0 is the one that we are all familiar with from LTE. That's the one with subcarrier spacing of 15 kilohertz and with slot duration of 1 millisecond. And that one has 10 slots per frame. So then we go on with doubling the subcarrier spacing. Numerology number 1 has a subcarrier spacing of 30 kilohertz. Then numerology number 2 is 60 kilohertz. Numerology number 3 is 120. Number 4 is 240. And number 5 is 480 kilohertz. But as we double the subcarrier spacing, then we have to halve the slot duration. Okay, those two are intervened. You know, when you increase the one of them, then you have to decrease by the same percentage. You have to decrease the other one. So if you are doubling the subcarrier spacing, you're halving the slot duration. And in the end, it really gives you a different number of slots per frame as you are changing numerology from 1 to 5. As you go higher with numerology, there are more slots per frame. And some of those numerologies are only to be used in frequency range 1, and some others are only to be used in frequency range number 2. I did mention that when it comes to latency, we would want to have, you know, some options which allows us to address our users more frequently, and those options are associated with the higher numerology. So as you see, we have more slots per frame the higher we go with numerology, which means that we can address more UEs per frame with a higher numerology. You can think of that slot as, okay, I am now going to be addressing, you know, certain user or maybe certain group of users in that particular slot. And even if it is just one user, which doesn't have to be, but even if it is just one user, then you can see that with numerology number 0, you would be able to address 10 users per frame. And then with numerology 3, you can address 80 UEs per frame. So it gives you more agility when it comes to addressing users to go higher in frequency. So it is to say that if you go to FR2, which is millimeter wave frequency, you can address UEs more frequently with those higher numerologies that are specific to FR2. Which really is going to be very useful, because if you remember, I mentioned that FR2 or millimeter wave is very good for deployment at large venues with lots of users, which is high density. So if you are in that environment, you would like to hop from one user to another with more agility. So that's why it is very good to have a large number of slots per frame, which is, you know, for that frequency and for that type of venue. Numerology choice affects the number of resource blocks per slot. Okay, so there you will see the number of resource block per slot for subcarrier spacing of 15, 30, and 60 kilohertz, which is numerology 0, 1, 2, at FR1 at lower frequencies. And there is a listed number of resource blocks per slot for FR2 for subcarrier spacing of 60 and 120, which is numerology number 2 and 3. So the question there is, why do we not see more numerologies? I'm mentioning here numerology 0, which is 15, numerology 30 kilohertz, which is numerology 1 and subcarrier spacing of 60, which is 2, and then finally 120, which is 3, but there is 4 and 5. This is taken from 3GPP documents, and they have defined it like this. So I'm just reporting as to what I have, what I'm seeing from the official document. There is some flexibility as to when you designed numerology, whether it goes to SS, synchronization signals, or other types of signals. They don't necessarily have to be the same, but this is what we are going to present now, and I don't really want to go into more details as to the variation of numerology with respect to which signal is present in the frame. So this is it for now. Then one of the new features is reference signals. They are different in 5G. In LT, we had a reference signal associated with cell-specific reference signal, or CRS. But 5G uses synchronization signal, SS, and channel state information, CSI, instead of CRS. So the question was, why did they have to eliminate CSR, RS in 5G? Well, the answer is to reduce overhead, because LTE reference signal has presence at fixed positions in 4 out of 14 OFDM symbols. And that is number one. Basically, we would like to reduce that there, and to basically improve the percentage of the payload that we can send, which is the number of PDSCH resource elements in a frame. And we are increasing the number of PDSCH resource elements per frame by reducing the number of reference signals that we have to send in that frame. The reference signals are not the only overhead signals, but they're the ones that were targeted to be removed and replaced in this revision of 3GPP. The second one is to reduce interference. Reference signals for LTE, they are mixed with PDSCH resource elements in 3 OFDM symbols. And thus, when you are trying to recover PDSCH from those 3 symbols, you have interference, because you basically have interleaved PDSCH resource elements with reference signal resource elements, and that creates some kind of a interference in between them. So by grouping those synchronization signal reference signals together in one portion of the frame, and not really trying to spread it out, over several OFDM symbols, we will be reducing interference. And as I mentioned, the only reference signal that is always transmitted is the one in synchronization signal block. So this is SSRS. And synchronization signal block has operator-defined repetition time. When I say operator-defined, basically you have to define that as a network operator. What is the repetition time for your synchronization signal block? And you have an option to go from 5 to 160 milliseconds. And each inode beam can have its own SS transmission slot, which is different from other beams. So that is another specific. So why would we want that? Why would we want to have a synchronization signal transmission slot to be different at one beam than from another? Because UE measures synchronization signal at various slot positions, predetermined slot positions, and reports back to eNode B. So based on those measurements, UE can say, all right, so at this particular position slot, I have measured the strongest SS block. And when that is reported back to the that is reported back to the base station, the base station then knows which beam is giving the strongest signal to UE, and that is the optimum beam for that particular UE, which is a very useful information. And that can be done in real time. Okay, that can be done in real time. So if UE is moving, then by measuring those predetermined slots, we can tell, in real time which base station beam is the optimum server for that particular UE. So SSRSRP is the signal coverage KPI for 5G. That's meant to say that if you are used to using LT RSRP heat map for 4G to determine whether you have a good coverage in the venue or not, then you will be doing the same using SS RSRP heat map. Okay. You don't have LT RSRP, but now you have SS RSRP, and that is your baseline measurement to figure out if the coverage is good in your venue. And then the last most important new feature is beamforming. In 5G, eNode B antenna has multiple narrow beams, and that is now a part of the standard. And those narrow beams, they can transmit on the same resource blocks to different UEs at the same time. And this is called frequency reuse with minimal interference. So I'm now showing you how those beams look like, and this is from a broadside, okay, of a 5G eNode B antenna. Each of those little beams will be active at a different time. They're not active all at the same time, because if they were, that will kind of defeat the purpose. We made them narrow because we wanted to isolate the signal. And we wanted to isolate the signal because we want to serve a specific UE. And so that's why those are narrow and they reduce interference as well. But there are two types of beams in 5G. There are PDSCH beams and there are synchronization signal beams. As you see, the synchronization signal beams are a little bit wider than PDSCH beams. There is a reason for that. SS beams are more of a, like, how would I say, beacon type of beams. Okay, you would try to catch as many of UEs as you can in within this one beam. And then once you catch several UEs in that wide SS beam, then you can use PDSCH beams to refine the position of a particular UE. But this is important to understand that if I have narrow enough beams, then I can transmit two or more at the same time to different UEs that are hopefully spread out. And when I do that, I use the same frequency on each of those multiple beams. And that is an equivalent of a frequency reuse. And the interference that there is in the network when you use this approach is fairly low, okay, which is a very big benefit for 5G. And that is the reason why they decided to go to trouble to construct a network, a cellular network with narrow beams to reduce the interference and to improve the spectral efficiency of the network, which means I can either serve more users or I can give better connection and higher throughput to the users that are already there. So having said that, I'm going to stop now and ask Kelly if we have any questions so far. I'm going to answer them before we continue.
Yeah, so we have a few questions here that we'll take. We can't take all of them because of time, perhaps at the end, but the first is, how is the frequency bandwidth allocated per beam? If we have 100 megahertz bandwidth, each sector / each beam uses the whole bandwidth, or are they using a percentage of bandwidth?
Yeah, it can be done both ways. It can be done so that you decide that each beam will have the same frequency band at its disposal, or you can decide, for example, to split the band into two and to assign one half of the band to some beams and the other half to other beams. We have seen it done as a suggestion done in both ways. Yes.
Okay. Which beam is used in the IB wave prediction, PDSCH or SS?
Okay, I will talk about that in the second half of my presentation.
Okay.
But in short, it is you, the user, who decides which beam will be used. There is an option in our antenna pattern where you basically say, I want SSB or I want PDSCHB.
Okay, perfect. Next question is, talking about beams instead of sectors, does this essentially mean the end of mechanical / electrical down tilt in 5G?
I don't think so. I have seen the examples of venue like basketball arena, for example, where you are putting your small cells above the audience, basically. And there is something in every venue that is called a catwalk, and that catwalk is very high up, and it is near the top of the arena. So you're going to be hanging those small cells from the catwalk, and they'll be pointing down. But you need to optimize where they're pointing, right? So you want to point them to certain section of the seating bowl that is below you. And to aim correctly, you will have to deploy the mechanical down tilt. That mechanical down tilt can be 0 if you want to point directly to basketball court down, if you want, or you can say 10 degrees off the vertical, or 20 degrees off the vertical, or 30 degrees off the vertical as you go higher and higher to the ball, right? So yeah, that is one example why the mechanical down tilt is still beneficial in 5G. And the second thing is, just finish this because this is a very interesting question. Second thing is this: not all those beams are created equal. What you are seeing here it is not obvious from this picture, but those beams that are directly in the broadside, which is the center of this variation pattern, they are narrower and they have smaller side lobes than the ones that are toward the edge of this sector. This is a 120-degree sector, and those that are right here are wider and have a higher side lobes than the one in the center, right? So you do want to point in the general direction where you want to have your users. If you don't do that, then you will expose the users to, I would say, the majority of users you will expose to your worst beams, worst as in the worst quality of beams. It will have the least amount of gain and the higher side lobes. So that is why you still want to down tilt your antenna in the correct direction.
Okay, and just maybe one last one before we move on to the next part, because I think some of these questions will be answered in your next part, Vladan. Is there a ratio between PDSCH and SS beams?
Ratio, like relationship?
I guess so, yeah.
Yeah. Well, we have not seen that. We just know that SS beams are wider. I have seen examples when, you know, the whole sector is just one wide SS beam. I have seen, you know, a situation which is more like this, but the rule of the fact is that SS beam is wider than PDSCH beam, which is, you know, a very wide rule. I mean, there is, you know, not much you are not covering when you are saying, I want SS beam to be, you know, wider than PDSCH beam. But other than that, there is no specifics as to how much wider.
Okay, thank you. So I would say let's move on to the next part where you cover the design piece a little bit.
All right. So the design piece. Well, we started talking about the beams and beam forming. So what is important to understand, you know, in our tool, if you want to calculate or simulate SSR-SRP coverage, which is your most important KPI, what you're really doing is you're basically saying, all right, I'm going to now assume that, you know, my UEs are spread out, and those SS beams, I don't know how wide they are, but, you know, and they're going to be transmitting, you know, every once in a while, and eventually all of those SS beams in node B will have been transmitted. You know, so what it means is that, you know, I really am interested in envelope of this radiation pattern, because if SS beams are there for coverage, and if each beam is going to transmit over time, then I really want to see the collective of the coverage of those individual beams, and that collective is the pattern envelope. And this is how that pattern envelope looks like in a horizontal cut and in the vertical cut. Horizontal cut is to the left and vertical is to the right. All right. But if you want more than that, if you want, for example, SANR, which is signal to interference and noise ratio, or PDSCH SANR, which is important if you want to calculate what is your maximum achievable data rate, then you need to define individual beams. Okay, you are not happy only with envelope, you need to define individual beams. So what I am now showing you is how it looks like in our tool in IBWave Design. Here in IBWave Design, you can have individual beams defined. Here is the SS beam, number 11. And you can see that there is number 11 here, and it says beam type SSB. And there you see that individual beams is defined in a certain direction in a horizontal cut, and with certain elevation in vertical cut. And there are some, you know, lobes here. It's not very clear, but they're there. And you do the same thing with the PDSCH beams. All right, now this is beam number 4. It is a PDSCH beam. Again, you know, it's approximately the same, you know, horizontal and the same vertical. So that is, you know, how we do that, you know, in our tool. We define the envelope, and then we define individual beams, you know, and then we have, you know, then we have an option to have valid SSR SRP heat maps, but also PDSCH SNER heat maps. So as for the best practice in the design, I am suggesting that every time when you have a small cell, which is 5G enabled small cell, to go into the part and double click on the part. And then there is an option to view antenna pattern. And when you click on that, then another window is going to open, and there you should click on the beam type, and then you should see both beam forming pattern and individual beams. If you don't see individual beams numbered, then it means that only beamforming pattern is present, and that means that only SSR-SRP is going to be available for your heat map calculations. You can still do SSSANR and PDSCH-SNR, but those calculations are not going to be reliable. They're not going to be valid. Okay, so your sanity check is go to double click on each part and go to view antenna pattern and go check if both beamforming patterns are and the individual beams are defined. The second best practice is to take a look at what is defined as UE, beamforming antenna gain. So far we talked about beamforming. We talked about beamforming at the base station or E node B. But what about UE? Does UE have beamforming? And the answer is yes, it does at millimeter wave frequencies. So just to repeat, there is beamforming at millimeter wave frequencies. And I have talked about that in the white paper. I'm going to repeat here. The information that I have gotten is from teardown reports on iPhone and what Samsung has said in some public presentations. But bottom line is there are each of those type 2 manufacturers, both iPhone and both Apple and Samsung, they have 2 RF modules at millimeter wave frequencies. Each of those modules is a 4 antenna linear array. So why do they have 2 modules? It's because of the polarization. Each of those 2 modules has a different linear polarization. One is plus 45, the other one is minus 45 degrees. And because there is a 4 antenna linear array, then we have 6 dBi gain. It is a pure antenna theory. If you have 4 antennas, then 10 logarithm of 4 is your gain. 6 dBi is what I'm suggesting based on the theory, and that assumes that your individual antennas have 0 dBi gain, because it is 6 dBi plus individual omnidirectional antenna gain. Samsung says it is not 6, it is 7. It is possible to have 7. It is possible for your individual antenna in array to have gain more than 0 dBi. So you can either put 6 or you can put 7. I'm suggesting you put 6. Now, the next topic is body loss. Now, body loss is higher at millimeter wave than at sub 6 gigahertz. And we, as in IBWave, we measured body loss with 2-person penetration to be in the 20 to 25 dB range. And if stadium antenna is mounted overhead, we think that 1-person penetration is more likely. And we think that 15 dB body loss is going to be more appropriate, okay, than 20 or 25. So our suggestion is to put 15 dB for body loss. And having said that, okay, it is, there is something to be said about the concept of having a body loss at millimeter wave and the concept of measuring the signal at millimeter wave. And I will touch on that subject a little bit later, but conceptually, if you think about it, what we have seen in at the lower frequencies, we would put 3 dB loss, and it is a loss, that you have because the signal is going through your head. And here, at millimeter wave, you really are not going to be using that phone to talk to somebody. Okay, it is mostly going to be used for browsing and watching the movie. So it's going to be away from your head. And that means there is a possibility that you may, at some point in time, have a signal that does not go through your body. Okay. And what do I mean by that? Well, it is if everybody is standing up and the game is really exciting, then yes, you will have 15 dB all the time. But if you are, trying to browse while people are still sitting down and maybe the stadium is half full, especially these days with restrictions of watching the sports games, then it is quite possible that you will not have that 15 dB penetration loss most of the time. So that is one difference when you are thinking about body loss between millimeter wave and lower frequency. At lower frequency, it will be there all the time, and it is only 3 dB. At higher frequency, it may not be there all the time, and it is much higher. It's 15 dB. So now, having said all that, this is what we have seen in the field. Okay, those field measurements were done at millimeter wave and in a large venue, and the measurements were done without, the audience, obviously. So the first thing that we have noticed is that absolute mean error is almost 6 dB, and the standard deviation is high. It's close to 7.5 dB. And at lower frequencies, LT measurements, typically the absolute mean error should be, less than 5 or around 5, so it's about 1 dB less. And the standard deviation is also should be about 5 dB, which is almost the 1.5 dB less. So why is this? Why am I seeing all this? So what we think is the case is we can make the case that some measurements are strictly line of sight as you are performing measurements in an empty stadium, and some are non-line of sight with the signal passing through that person who is taking measurements. Right? So sometimes your body is basically you being used as a obstacle for the signal that goes through the UE, and sometimes it is not. And so we wanted to take that that notion to test. We basically took out the data points where we thought there was excessive loss at the tune of 15 dB or more, which we would assume it is additional body loss, right? So when we took them out, the statistics looked like what you see before. Absolute mean error, just around 5 dB, standard deviation just around 5 dB. And as for the statistics, I would say it was about 15 to 20% of those points with the excessive loss. Excessive as in, 15 dB or more than what I had expected. When I say I had expected, meaning I started these measurements by assuming that I had only 3 dB loss, body loss, which is the same as for lower frequencies. But when I took out, the points where I had 15 dB or more loss, then I got the statistics that you see below. So the conclusion is 15 dB is what I should have as a body loss. And when I do that, then my statistics are going to start making more sense. So that is why we suggest putting 15 dB body loss in there for your design. Then the next thing is transmit power modeling. Now this is an interesting one. I'm now giving you an example from an OEM small cell, and there is lots of information written there. And I'm going to now walk you through how to make sense of it all when you want to use that in IBWave design. So they are basically saying that you can have you can cover up to 800 megahertz of a bandwidth, and you can do that by using RF channels of 50, 100, or 200 megahertz. So obviously, but how many? Okay, so they say you can have up to four different what they call component carriers. So 4 different RF channels. So if those 4 different RF channels are 200 megahertz each, then you will cover all of 800 megahertz. If they are 100 megahertz each, then you will cover only 400. If they are 50 megahertz each, then you cover only 200 megahertz. But they also say something like, yeah, you can have 8 RF beams. And so what does that exactly mean? Well, it really means that you have eight amplifiers, right? And those 8 amplifiers are spread out for different channels. So you can have 2 amplifiers per each channel. And each amplifier is going to beamform one particular polarization. One will beamform plus 45 degrees, the other one will beamform minus 45 degrees, right? So you have, 4 different amplifiers, spread over 4 different channels. And then they will basically say your ERP is 51 dBm per beam. So so I have 8 different beams, and each one has 51 dBm EARP. Because I have 8 of them, and 10 logarithm of 8 is equal to 9 dB, the total is 60 dBm per radio. So the total EARP is 60 dBm per radio, or 51 per beam. And then there is something in small letters that is important. Okay. So what do they say in those small letters? They're basically telling you that yeah, what we told you here is correct. You can have 51 per RF beam, but you can lower this power by 6 dB and still have correct operation of the small cell. When they say correct operation, that means everything is functioning the way it should be. Yes, you have reduced your power by 6 dB, but all the electronics are operating correctly. And yes, your coverage will be less if you reduce by 6 dB, but you can do that without endangering the total operation of your small cell. So what I'm now saying of all of this, EIRP per path in IBWave design can be between 45 and 51 dB range. So that is what you see from this table. So then what you do is you perform another sanity check. Go and into OEM part and take a look at 2 things, well, 3 different things. Take a look at the power per channel. Take a look at the antenna gain. Add those together, okay? And then see what they are. In this example, it is 45 dBm. And I told you on a previous page that EIRP, based on the specs, should be in the 45 to 51 dBm range. So this is correct, okay? This is modeled correctly. The power that you have per beam is in the correct range. Then finally, take a look at how they defined the signal, okay? They basically said, I have a 100 megahertz channel, and there will be 4 channels, which means that I'm going to have 4 100 megahertz channels. And there I said configuration is 2 by 2 MIMO. Remember when I was telling you about plus and minus 45 degree polarization, where that's that. Basically what this is telling you that you're going to have 8 RF beams, and those 8 RF beams will be spread out 4 different channels, and each channel will have 100 megahertz. So you are covering a total of 400 megahertz here. So this seems to be a little bit tedious, but it is a good practice for you to go in and take a look and see, if everything is modeled correctly. And in this case, it is. Then there are a couple of interesting things that I want to mention. This is a near and far field boundary. So what is this? Basically, there is a formula that is given in electromagnetics theory then based on the largest linear dimension of antenna array and the wavelength, you can find what the near and far field boundary is. And I'm just giving you two examples. If you see a panel that is half meter along this diagonal, then you can have very different values at 3.5 and 30 gigahertz for near and far field boundary. Interestingly enough, the higher you go in frequency, the boundary gets larger and larger. And so this looks like 50 meters. It is a very, very long. So what do we do about it, and why do we care? Well, first of all, let's see if what I have said in the previous page is true. And to tell you straight up, it is not, because when you open the panel, the antenna array is not going to be spread out over the whole panel. It will be grouped into a tighter space. Let me give you an example how it looks like if you have only a single panel or if you have 4 panels, right? Now this on the right is more realistic at millimeter wave. At millimeter wave, you may have multiple antenna arrays under a panel, and each one is going to have this diagonal that is going to be of the order of maybe 10 centimeters, right? So not 50 centimeters, 10 centimeters. So if you put 10 centimeters in there, you will have much different results. You're not going to get 50 meters, you will get something like in the order of maybe 4 meters. So how do you figure out what is a near far field boundary? You can do it by opening the panel and measuring this distance, or if you don't want to or need to open the panel, you can do it by measuring the power. You measure the power, broadside, line of sight of the small cell, and you measure that while doubling the distance between antenna and the measurement equipment. You start at 1 meter and then 2, 4, 8, 16. And then when you see that the power drops by 6 dB in between consecutive measurements, that means you're in a far field zone. So that is how you can do that in the field. And so why do you care about that? It's because you do not want to have anything metallic in your near field. And why? Because that will severely affect your antenna radiation pattern. So do not install your antenna like this. This is a bad example. Okay, you have lots of metal in the near field. Your antenna radiation pattern is not going to be happy if you do that. And we call this exclusion zone number 1, which means there may be exclusion zone number 2, and that is for EMF radiation compliance. So in the small cell example, that I have given you, combined EARP was 60 dBm. Okay, that is a lot. Okay, and not only that is a lot, but oftentimes you have multiple radiation sources from the same location. So it will not be just this small cell millimeter wave antenna that has 60 dBm EARP. There may be multiples, right? So what you need to do is you need to calculate, what your radiation compliance distance is when all networks are active, 3G, 4G, 5G, Wi-Fi, and so on and so forth. And you need to be aware that your millimeter wave will be a significant contributor because of the large EARP. Now, when you figure out what that compliance distance is, that is your exclusion zone number 2. Now that you have exclusion zone number 1 and 2, you need to basically figure out which one is larger of those two and try to find locations in the venue where you can have a clearance between your antenna and the larger of those two exclusion zones. Now, as for millimeter wave propagation, I can tell you that we have seen that there are 2 types of materials as far as propagation at millimeter wave. There are heavy and dense materials such as concrete and brick, and they will not let millimeter wave signal through. But there are light indoor materials like sheetrock that may let the signal through depending on a few factors like distance, how many walls in between the transmitter and receiver, and so forth. We also seen that some flat indoor objects reflect millimeter wave signal very well, such as whiteboard or large flat screen or TV or large mirror. So the best practice would be to design indoor millimeter wave networks as strict line of sight and choose venues with high user density and line of sight, such as conference rooms, cafeterias, stadiums, and conference centers for your millimeter wave networks. And don't forget to model highly reflective objects if they are larger than 1 meter. And to summarize, what I've told you is, as a best practice is number one, you check your E-node B antenna pattern for individual beams. Are they defined? Adjust UE gain to account for UE beam forming, which is 6 to 7 dBi. Set body loss at 15 dB and make sure that EIRP per path is in the specs range. So you have to have access to the manufacturer's spec sheet, and you have to have access to how it is modeled in IBWave design. Always determine antenna exclusion zones 1 and 2 before site visit. And at the site visit, I first identify the potential transmitter locations with the building manager based on those exclusion zones. And only after those locations are determined, then run prediction and finalize the coverage scope with the building manager. You do not want to promise the building manager that he will or he or she will have coverage in the areas where they cannot possibly be because of the restrictions of the antenna locations. And those restrictions are imposed because of the exclusion zone number 1 and 2. And only use line of sight design for targeted coverage area for millimeter wave networks. Don't forget to model highly reflective objects if they are larger than 1 meter. Having said that, I'm now going to just briefly give you an example of the design, office design with the millimeter wave. So first, what do we have here? I have an area which is cubicles. I have also area that is, as you see right here, it's a boardroom, right? And this is a reception desk, all right? And this is, the hallway that is connecting, the entrance, the reception desk, with the boardroom and the second portion of the building. So where do I want to put my antennas? I'm expecting the highest density of the users right here. And I also have only those separation walls for cubicles, which are not very high. So I can have a good line of sight here. So if I decide to cover this area, I should have good line of sight. Here, it's strategically important that I have the high throughput because of the guests that are coming to the office. The guests are also here as well. So I would want to have a very good connection with the high throughput. And this is a connection area, so I want them to have a coverage from here to here. So let me show you how it looks like on a 3D plan. Right, so you see here are my transmitting antennas covering the cubicle area. And this is my antenna covering the boardroom. And this is the antenna covering the entrance, and this is the corridor in between the entrance and the boardroom. So I have decided strategically to only focus on the areas where I either expect a lot of users or I expect very important users. Having said that, we can go into the properties to make sure that we did what we said that we should do, and that is to mind our body loss and antenna gain. Again, antenna gain is 6 dBi, body loss is 15 dB. So with that in mind, I ran the simulations, and you will see that, and I'm gonna give you a probe here. So you see that we have a decent coverage here in a cubical area where there is a line of sight between those antennas, 1, 2, 3, 4, and employees that work there. Green is good. We also have green here at the entrance and in the hallway and in the boardroom. But what we see is the signal drops. The signal drops whenever they see the wall. Okay. Some signal here, as you see, because it went through the door, but here in the shadows, not very good. So essentially, when you have an office, you see you cannot really have the very good coverage everywhere because you have individual offices and the signal really will not go through those walls, right? So if you want to have additional coverage in the cafeteria, you will need another antenna here, another conference room, another antenna here, and so on and so forth. You pretty much have to have, in every room where you need coverage, you need to have an antenna. So having said that, this is the end of my presentation, and I'm going to now turn over to my colleague, Kelly, to complete this presentation with questions and comments.
Sure. Thanks, Vladan. So we have a lot of questions here. So I just going to apologize up front. We're not going to have time to get to them all today. We'll try to come out with a piece of content or get back to you guys individually with answers to some of the more common ones for sure. And I just wanted to briefly mention here that if you're interested in learning more about 5G, we actually have a promotion going on right now for our 5G training course. It's about a 6 or 7 hour course. And the link is there. If you go there, then it'll tell you all about the course, and you can get a 25% discount there. Okay, so I'm going to jump into the questions here. I'm also going to throw a poll up on the screen. If you guys could answer that while we answer questions, it'd be super helpful for us to help focus our next 5G content on what you want to learn about. So I'm just going to launch that now and ask some questions here. So Vladan, one of the questions here is, does cell loading in 5G have an impact on SINR like 4G LTE?
That's a good question. Yes, it will have but through different means. It will have the impact in the point of to how UEs are grouped, and we will answer that when we introduce Monte Carlo in our simulations, but not exactly in the same way as it was in LTE.
Okay, thanks. What propagation model is used by IBWave for the 5G indoor coverage?
We are still using ray tracing. We are not using a one slope model, if that is what the question is about. Basically, we are going to distinguish our rays in between transmitter and receiver into three different groups. One is line of sight, one is reflected paths, and there is diffracted paths as well. So the signal at the receiver is the summation of those three. Maybe not all three will exist at every pixel, but in general, those are the three types of the signals.
Okay. How do you determine which beam to use and in what circumstances for PDSCH and SS?
Okay, so what you are seeing right now is in our tool. we are assuming that we have an analog beamforming. So analog beamforming is going to have only one beam at a time for PDSCH. Now, for having said that, what you are doing here internally, what we are doing in our tool, when we run RSRP prediction, SSRSRP prediction, we are using SS beams, right? Characteristics of SS beams, which means to say if you define your SS beam to be, I don't know, 30-degree wide, 60-degree degree wide, with the gain of, I don't know, 15 dB or 17 dB, we're going to use that, and we're going to use an envelope of those SS beams to calculate SSR-SRP. So that is done internally. You, as a user does not need to do any intervention, any setup in our tool to say, I want SS beams. This is done internally. Now, if you go on to calculate PDSCH, SANR, and MADR, then we are going to internally switch to PDSCH beams and the characteristics of those PDSCH beams with a specific beam width, with a specific gain, and so on and so on. So this is all done internally. This is not does not really require a user intervention.
Okay, great. Unfortunately, that takes us past the hour, so we're going to have to stop our questions here. But like I said, we're going to try to group some of the more common questions together and then get them out there for you guys so you can get your answers. So a big thank you to everyone who joined us today, and to you, Vladan, for sharing your knowledge with us on 5G. Like I mentioned, we do have a promotion going on right now for further 5G training. If you're interested, it's ibwave.com/5G training. You'll find all the information there. We will send out a recording and the copy of the slides for you. So thanks very much and have a great rest of your day.
Thank you very much, Kelly, and thank you for giving me this opportunity to share what we did in 5G in our tool with our captive audience.
Great. Thanks, Vladan. Take care,
Bye-bye.
everyone.